In our video today, we're going to look at a pretty typical free response question that you might see on the AP exam involving motion along a curve. So we have an object moving along a curve in the xy plane. It has position x of t, y of t at time t with dx dt equal to sine t cubed and dy dt equal to cosine t squared. So we're starting out here at the velocity vector level. We're given the derivative of each component of the position vector. At time t equals 2, the object is at position 7, 4. The first thing that we're asked to do here is to write an equation of the tangent line to the curve at the point where t equals 2. Now, when we do tangent lines with parametric equations, we've got to be really careful about the variables and the values that we're subbing in for the different parts of our tangent line equation. We want it at the point where t equals 2, and I think a lot of students are really tempted to use that 2 as our at number. Let me just write out our preferred tangent line formula looks like this. And we're tempted to plug that 2 in for the a, but that a value should be an x number. It should be the x coordinate of the point of tangency, and the f of a should be the y coordinate of the point of tangency. This is just the moment at which we want this information. If we look up here in the prompt, they told us at time t equals 2, the object is at position 7, 4. So this 7, 4, that is my a, f of a for the tangent line. And so what I need still is the f prime of a, which is going to be the derivative at that point. Or the dy dx at the point 7, 4. So remember that when we do a derivative in parametrics, this is going to be equal to dy dt over dx dt, again at the point 7, 4. So I failed to point this out when we started. This is a calculator free response question. And so I'm going to model this on the Inspire, but the things that I'm doing here, you can also still do on Desmos as well. It works pretty similarly on Desmos. So I'm going to open a new document with a calculator page, and I'm going to add a graph page. And in the graph page, I'm going to enter the two functions. So f1 of x, I'm going to let that equal sine of x cubed, keeping in mind that my x here is really a t in my problem. But when we enter things in on the graph page, we can only use x's. And then in f2, cosine of x squared. Okay, so there's my two components of the velocity vector. So now I'm back on the calculator page, and I need dy dt at the 0.74, which also means, actually, I guess I should have written, because my dy dt and dx dt, they're in terms of t. At the 0.74 also means at the time t equals 2. Like all of those things occur at the same time. So I'm going to do, to get my slope, f2, because I'm starting with dy dt on top, and dy dt is what I entered in f2. So f2 of, and my t value is 2, over dx dt, which is f1, and I'm going to plug in 2 to that as well. And so my slope here is negative 0.6606. And so with that, we have what we need to write our tangent line equation. y is equal to the y-coordinate of the point of tangency, which is 4, plus the slope, negative 0.6606, times x minus the x-coordinate at the point of tangency, which is 7. Okay, moving on to part B, we're asked to find the speed of the vector at t equals 2. And so we need to remember that our speed formula, speed is the absolute value of velocity, or in motion along a curve, it's the magnitude of the velocity vector. And of course, that's going to use Pythagorean theorem. Square root of dx dt squared plus dy dt squared. That's our speed formula. So the speed at t equals 2 is going to be the square root of dx dt squared, and our dx dt is sine of t cubed. And I'm going to plug in 2. That would just be sine of 8 squared. I guess I could have done this on part A also. And then dy dt is cosine of t squared, so that would be cosine of 4 squared. And technically, we could leave it in that form. I could also have done this in the calculator. If it was a more complicated function where you couldn't just easily plug in the time, we've got the functions in the calculator. And so I could have done f1 of 2 squared. Actually, I probably need that in parentheses. Undo. There, f1 of 2 squared plus f2 of 2 squared. Whoops, I didn't get it outside the parentheses. Outside, there we go. And so we get 1.1857 for the speed. All right, for part C, we get to, it's probably the most challenging part of this question. For what value of t between 0 and 1 does the tangent line to the curve have a slope of 4? And then we want to find the acceleration vector at that time. So let's start here. When does the tangent line to the curve have a slope of 4? So that means what I'm looking for here is, when is dy dx equal to 4? That's what I want. Well, remember that dy dx is dy dt over dx dt, which is sine t cubed over, oh wait, no, I think I got that backwards. Sorry, I should have gone back and looked. Yeah, I got them switched. Sorry. Dy dx is equal to dy dt, which is cosine t squared, and dx dt, which is sine t cubed. Sorry, I wanted the sine to be on the y, and it's not. It's on the x. Okay, so this is our slope. We want that to be equal to 4. Now, this is a calculator question, and so this is something that we can solve this equation on our calculator. I generally prefer to do that on the graph page. Excuse me. And I'm going to do a new page, a new graph, a clear graph. And I'll type in my slope, which is cosine of x squared. Or remember, I do have this saved in F2. I could have just done F2 of x over F1 of x if they were complicated functions, just to save a little calculator energy. But there's the slope. Pretty intense. And we want it to be equal to 4. And obviously that happens many, many times. But in the question, they said we want the t value that is between 0 and 1. And so it's going to be that value, that intersection point right there. And so I'm going to menu, analyze graph, find intersection point, and there we go. Intersection is at 0.616. Now, that's really not, I need more decimal places than that because I need to plug it into the acceleration vector, and so we don't want to lose any accuracy. And so what I'm going to do here is click on that x coordinate, and we're going to save it as a variable. I'll go ahead and call it t. That's our time. Enter. And so now I'm going to go to a calculator page. I'll just add a new page here. And if we want to just check, I'm going to type in t, and you can see now I've got more decimal places there for that point. So we're preserving the accuracy. What I want now is the acceleration vector at this point. The acceleration is going to be the derivative. My acceleration vector is going to be equal to x double prime of t, y double prime of t. Remember, what we were given was dx dt and dy dt, or x prime, y prime. So I just need to take the derivative of both of those. And I can use my calculator. Use my calculator to do that. My x prime is in F1. And so I'm going to do menu, calculus, derivative. And the value where I want the derivative to be taken is at this t value of 0.616. So I'm just going to type in t here and say OK. And then the thing I want to take derivative of is f1 of x, because that is my dx dt, or my x prime. And 1.1090. And then we're going to do the same thing for y prime or dy dt. Menu, calculus, derivative. My value is t because we stored it. And I have this saved in f2 of x. So that's negative 0.4573. And this is all the work that we need to show here. It is a calculator question. I'm showing that I know the acceleration vector is the derivative of the velocity vector, and then we just did the work in our calculator and found our vector. All right, our final question here. Find the position of the particle at time t equals 1. So to find position from velocity, let me just write, I'm going to write our velocity vector here. And I'm going to get it right this time. Sine t cubed cosine t squared. Okay, that's our velocity vector. To find position, we need to integrate, but we also need, if I just integrate each of these components, it's going to give me a displacement, a function representing displacement. And what I want is the actual position, and so I need a starting position. Remember, at t equals 2, position is, we're at 7, 4. So to find my x position at 1, x of 1 is going to be equal to x of 2, the one that I know, plus the integral of sine t cubed dt. Now here's what's important in labeling our integral here. We have to start at the time that we know, and we have to end at the time that we want. It's a little bit awkward because we're actually going backwards. We're starting at t equals 2 and we're going backwards to t equals 1. My integral needs to reflect that same thing. And let me go ahead and write the y. Y of 1 is going to be equal to y of 2 plus the integral from 2 to 1 cosine t squared dt. And then we can just do both of those integrals in our calculator. And what is, sorry, I should have put in the numbers. X of 2, this is 7, and this is 4. So 7 plus the integral from 2 to 1. I could type in the function, or again, remember I have it named f1 of x, and I can use that as well. And then 4 plus menu calculus integral from 2 to 1. This one is in f2 of x. And there we have both coordinates. So the position vector at t equals 1 is 6.7818 and 4.443. I'll just stop at 3 on that one because I ran out of room there on my paper. Sorry about that. So pretty typical parametric motion type free response question. You're going to do a couple of those today for practice.